Now we get to another type of calculation in which we're given starting amounts, we're given K, and we're asked for the equilibrium amounts. So here's our SCA chart. We start with HI, 1 atmosphere pressure, no H2, no I2, change minus 2x and x, just the normal old thingies, x, 2, 1, 1, and then use up reactants. So at equilibrium, 1 minus 2x, x, and x. The equation, 2HI reversibly goes to H2 plus I2, so therefore Kp is the pressure of H2 times the pressure of I2 divided by the pressure of HI squared, because that's coefficient of 2. Pop in what we know. We know that Kp is 0.016. We've got all of our equilibrium pressures in terms of x. We don't know x, but that's fine. We can just use maths to solve x. So this is the end of chemistry and the start of maths for a little while. We look at this expression and we see that we got x squared on top, 1 minus 2x all squared on the bottom. So we can square root of both sides and we get this. Multiply it out and work it through just like expressed here. So we first of all bring the 1 minus 2x up here, multiply that out, bring together the x terms, and we get overall x.1. Now how does that help us? Well, we asked for the equilibrium pressure of HI, which is 1 minus 2x. So thus the equilibrium pressure of HI 1 minus 2x, x is 0.1, so it is 0.8 atmospheres. So this one looks relatively straightforward. We've got a nice easy 1-to-1 to 1-to-1 reaction. We're told Kp for this. Reaction is initiated with H2 and CO2. Well, hang on a minute. H2 and CO2 are on the right hand side. What gives? Well, here's where we can set things up quite nicely by just remembering that K is the ratio of the righties over the lefties. Well, right now we got the righties. And what we want is the lefties, because that's what we know the starting point as. Well, the nice thing with an equilibrium situation is it's got there by a reversible reaction, and we can write reversible reaction in either way. So why don't we just write this the other way around? So we got the CO2 and H2 that we start with on the left-hand side. Well, as we flipped the righties and the lefties, we're also going to flip the top and the bottom of the Kp. Okay, write an equation the other way around, flip Kp, because what was righties is now lefties, what was lefties is now righties, and Kp is of course righties over lefties. So righties over lefties becomes lefties over righties, 1 over that. So Kp is actually 1.5625. Well, now we can just proceed in our usual way. There's our SCA chart. 0.63, 0.63 of the H2 and CO2, none of the CO and H2O. So Kp for this new one, which was of course 1.5625, is CO times H2O divided by CO2 and H2. Plug in we got x times x, 0.63 minus x, 0.63 minus x. Square root both sides, and we get 1.25 is equal to x over 0.63 minus x. Multiply all that out, that's the maths, and x is equal to 0.35. What we asked for? We were asked for the partial pressure of CO at equilibrium. Well, that is equal to x, so therefore the answer is actually x, 0.35. But aqueous solution, A and B react to form 2C, so let's write that out with pretty colours. K is equal to 100, so we know K is going to be C squared over A and B, all of these of course at equilibrium. We're prepared in which the initial concentrations 1, 1, 0, so we know the starting concentration, we're asked for the equilibrium A. So again, set up our SCA chart, make sure you see where everything comes from. 1 each of A and B, none of C at the start, 1, 1, 2 in the stoichiometry, so therefore minus 1, minus x, and 2x. Plug it in, 1 minus x, 2x. Pop everything in, we know K is 100, we got 2x all squared over the top, 1 minus x times 1 minus x on the bottom. Square root both sides to get 10 is 2x over 1 minus x, multiply it all out, so we get 10 minus 10x is 2x, so 10 is 12x. X is 0.83. Well, is that the answer? No, because what is the equilibrium concentration of A? was the actual question, which is 1 minus x. So the equilibrium A is 1 minus x, which is 0.17. 21. Ammonium iodide can dissociate, produce air, so it's a nice little solid here. So there's that. Let's set up our SCA chart. And again, NH4I doesn't factor in here because it's a solid. So we start off with some of that because, of course, we need it for the reaction. Repeat it 300, blah, blah, blah. What's the partial pressure? We don't really care about the temperature. We don't care about the volume. We're just interested in the pressure. So we start with none of the NH3, NHI. Therefore, they each change by x. So at equilibrium, we have x of each. Looking familiar, right? Kp is the pressure of NH3 times the pressure of HI. Kp is 0.22. Each of those is x. So therefore, x is the square root of 0.22, which is 0.469 bar. The opposite of the last question we did, in which, of course, I gave you a way to get the x, and that way you could get k. Here I tell you k, so all you got to do is figure out x. Now a question that is nice in 3 ways. The first thing is it introduces an important concept that we will actually apply conceptually when we start talking about weak acids and to a lesser extent weak bases. Second thing is an indication that you must not panic just because you see something weird. And finally, it's actually a relatively straightforward question when you cut through all the goop. So anyway, we've got Kp for a reaction in air. We are told that the pressure of N2, which is one of the reactants, and O2, which is the other reactant in air at the start at 0.8, 0.02. So we're given Kp, we're given starting concentrations, we're asked for an equilibrium. So set up our SCA chart. Okay, and it's actually Kp's, of course. N2 is 0.8, O2 is 0.02. We have no NO. It's a 1:1:2 reaction. So therefore 0.8 minus x, 0.2 minus x, and 2x there. There's the Kp expression, throw everything in and we get this. Now at this point, we could solve a horrendously yucky quadratic equation, or we can think like chemists. K is really, really small. Now if K is really, really small, that means you don't have very many products, and as this is so teeny, you've got a teeny amount of products. So what that tells you is that x, or 2x, is a really small number. Now, if x is a really small number, we can make this a lot more simple by assuming that when we take x from 0.8, it's about 0.8, and when we take x from 0.2, it's about 0.2. So we rewrite the equation like this. Much easier to solve, and I'll be having extensive discussions in our acid-base conversation, by the way, about this assumption time. Anyway, solve it, and we get x squared is 0.8 times 0.2 times 1 times 10 to the minus 7 divided by 4. So x squared is this. X is 6.3 times 10 to the minus 15. Now at this stage, pause and ask yourself, was my assumption valid? Is 0.8 minus x about 0.8? Well, 0.8 minus x is 0.799999999999994. I think we can say that's 0.8. So anyway, x is 6.3 times 10 to the minus 15. How does that help us? Well, because we know that the pressure of NO at equilibrium, which is what we wanted, is 2x. So it's 1.26 times 10 to the minus 4 atmospheres. Now that's the pressure of NO at equilibrium, but we wanted the concentration of NO at equilibrium in this weird unit that nobody's ever seen before. Well, if the last sentence hadn't been there, we'd be totally up a gum tree. As it is, though, we're told, well, in 1 atmosphere, there's atmospheres, there's 2.46 times 10 to the 19 molecules per cubic centimeter. So therefore, all we have to do to get the NO in molecules per cubic centimeter is multiply this by 2.46 times 10 to the 19, and we get 3.11 times 10 to the 5 molecules per cubic centimeter. So another fun question, when you first look at it, you think, oh my goodness, what is going on? But then it actually gets a little bit more straightforward. So anyway, that's our reaction. CaCO3 solid goes to CO solid plus CO2 gas, which means that every calculation we have to do associated with the equilibrium simplifies because it only concerns CO2 gas. So we start with just CaCO3, heat it up, and so we get some reaction. So we start with no CO2, we'll have X amount of reaction, so we will have X CO2 at equilibrium. Now, what is X? Well, we're told Kp is 1.16. Kp is, of course, the pressure of CO2 at equilibrium, because that's the only thing that's in there. So the pressure of CO2 at equilibrium is 1.16 atmospheres. How does that help us answer the question? Because we're actually told some other stuff, and then we're asked about grams of CaCO3. Well, 1 mole of CaCO3 will make 1 mole of CO2. So therefore we need to know the moles of CO2 so we can get the moles of CaCO3 and hence the grams of CaCO3. How do we do that? Well, we go back to PV equals nRT. We know the P, we know the V, we know R, because I tell you it, because our pressures, our units are weird for pressure and volume, and of course I know T, 600 Celsius. So applying all our knowledge of gases, pressures 1.16 atmospheres, volume 10 litres, N we don't know, R because we've got litre atmospheres, 0.0821 litre atmospheres per mole Kelvin, and temperature 600 plus 273, 873. Work all that out and we get that there are 0.162 moles of CO2 made. Now if there's 0.162 moles of CO2 made, there will be 0.162 moles of CaCO3 used up. And the molar mass of calcium carbonate is one of the nicest ones out there. It's 100, as long as you go to just the nearest whole number. So 100 grams per mole times 0.162 moles means that we have used up, reacted 16.2 grams of calcium carbonate. Fun, fun, fun when you cut through all the verbiage.